what we're going to look at is, as I said, using differentials for local linear approximation. And a linear approximation is if you zoom in on any point, as I showed you on the calculator, and the graph, because I've zoomed in so close, actually looks like a line, even though we know x squared plus 1 was not a line. It's clearly a parabola. So we are picking some given point x comma y, which is x sub 0, f of x sub 0, and we want to approximate at that point. Okay, so what they're showing you here on the graph is that if I were to zoom in on this point, or this one, or any given point, the graph actually looks like a line. I'm zooming in on whatever that point is. So what we have is our function, f of x. Okay, and this is what we're talking about in terms of local linear approximation. And we want to evaluate f of a, some given point. If we have an equation of a line that is tangent to the curve that we are using for our linearization, which is L of x, all we have to do is plug into the equation of the line. So I'm going to give you all the steps, which actually, you guys have done this before. This is nothing new from Unit 1. I asked you, if we wanted to find an equation of a line that was tangent to a curve at a given x value, we could totally do it. You told me exactly what to do. So these are the steps. You have the point-slope equation. This is what you want to use. We would then solve for y, meaning once we had our slope and our x and our y values and we plugged into the point-slope formula, we would have this equation. We want to solve for y. So that means we take this y sub 1 value and either add or subtract it, depending on the sign, and move it over to the other side. Then you have all of this crazy mathematical notation. Here this says that f of x is approximately f of x sub 0 plus f prime of x sub 0 times x minus x sub 0. Okay, it's just notation. It's nothing that you haven't used before, but this is the formal notation for the local linear approximation. Big deal. Okay, we can totally do this. So the only difference now is, because we are using what's called linearization, your notation for this equation is going to be L of x. All of this is everything that we have done before. So L of x is essentially y sub 1 plus m times x minus x sub 1. That's what all that fancy f of x sub 0, all that stuff means. It's everything that we've used before. The only thing we're doing is, with our point slope formula, is we're making it look a little bit fancier. Instead of y equals, we're giving it the title L of x. That's fine. We can do that. There are, however, some discrepancies in the value that you get once you plug in. Sometimes you are either over or underestimating, depending on what the curve looks like at that given value. So the value you find is considered an overestimation if your original function is concaving down, which we will indicate by CD, okay, concaving down, okay, and the line that you are using to approximate the value is above the graph. So this is what we've got. We've got a graph, okay, and the function that we are given, f of x is equal to whatever our function is, that portion is concave down. So they want us to evaluate or approximate f of, we'll call it a for now, okay, which we'll say is at this point. When we find the equation of a line that's tangent to the curve at this given point, what's going to happen is that line is going to be up here. Okay? So this is our linear approximation formula. This is f of x. Any value that we choose right here where the curve is concave down will always be below the linear approximation formula. Okay, so what we're saying is that L of x is greater than our original function. So the problem here is when we plug in the value that we're looking for, we're going to get numbers up here that are greater than our original function. So we are using an over approximation to say this is what this value is equal to. Does everyone understand what I'm talking about? So this will happen when L of x, meaning your linear equation, is above f of x, and the reason is because f of x is concave down. If you were asked to justify your answer, this is the justification. Okay? All right, so now we're actually going to talk about what would happen or occur that would give us an underestimation. So when we're looking at an underestimation, this is when we have a function, whatever is given, okay, and the area that we're looking at is concaving up. So we're actually going to use... Thank you. An underestimation, and thank you all. The graph is concaving up, so we'll use this notation, okay, just like before. Okay, and what happens is the linearization or the linear approximation falls below this curve. Okay, so here we have a graph that's going to be concave up. We've got our graph, just like this. So just that portion of the graph is going to be concave up wherever we're looking. And then what we have is our linear approximation would fall below, just like this, wherever we're looking. Oops. Okay, so this is f of x. This right here is L of x. And if we're looking, let's say, we'll call this A, just like we did before. Okay, what we're looking at here is that L of x is less than f of x. Okay, and any value that we use this linear approximation formula to find for f of x will fall completely below. So what that means is that these values will all be under the true value. And I'm going to show you what happens when that occurs. And your justification would be that f of x is concave up. Okay, if you were asked to provide a justification. So please make sure you're reading the questions clearly, especially if you're working on an FRQ. Okay, so that way we can answer what they're asking and not give too much information. Okay. So a lot of this is not really going to make a whole lot of sense until we actually do a problem. So that's what we're going to do